So, let's briefly recapitulate on a few things we mentioned last time. Well, firstly, I remind everyone that there will be an opportunity to give talks, and last time I mentioned two potential topics. Topic number one is Brown's representability theorem, and topic number two model structures and spectra, which basically means we first introduce a naive model structure, which doesn't quite give us what we're after, and then we Bausfeld localize it to get the stable model structure. So, well, this is something to think about. We're not in a hurry, but it would be a good idea to cover one or both of these in class. Okay, so another thing we mentioned last time. We saw what an omega spectrum is, and how exactly an omega spectrum or a mega spectrum, not sure about the stress, gives one a cohomology theory for spaces. Today we'll talk a little bit about cohomology theory for spectra. Now, let me briefly recall that omega spectra are precisely the fibrant objects in the stable model structure, which sort of indicates that omega spectra are not just a random notion, they are natural. It's not just a random notion which somehow, for some strange reasons, gives one cohomology theories. It's a natural notion from the perspective of the homotopy theory of spectra. Okay, does everyone remember what an omega spectrum is? Good. So, CW spectra, which we'll talk about in a minute, are, on the other hand, the cofibrant objects, both in the naive model structure and in the stable model structure. So, in particular, if we have a spectrum which is both a CW spectrum and an omega spectrum, then it's both fibrant and cofibrant, which makes it appropriate for calculating morphisms in the homotypic category. Suppose we have a spectrum, it's a CW spectrum. If all components are CW complexes, and what? And each map sigma xn into xn plus 1 is an inclusion of a subcomplex. Now, here we take the reduced suspension, meaning we take the usual suspension and then we collapse the base point across 0, 1, which does not affect the homotype type because 0, 1 is contractible. This map is part of the data. Now, in general, this is just a map. Let's assume that this map is an inclusion of a sub-complex into a larger complex, and then we get the notion of a CW spectrum. Well, we already have an example. We we have the suspension spectra of spaces which have this form of axis CW complex, and as we'll see later, and if once we have those, we can also shift those to the left or to the right. And we will see that if a spectrum, a CW spectrum, has finitely many cells, then this is all there is. CW spectrum with finitely many cells are precisely shifted suspension spectra of finite CW complexes. Okay, so what's the next thing I wanted to talk about? Well, since we have since we sort of know or suspect that these spectra will be cofibrant, it makes sense to ask what the notion of homotopy or left homotopy we will have for maps out of CW spectra. Okay, so we We secretly know that in order to construct a sensible notion of homotopy, we need cylinder objects if we map out of cofibrant objects, or path objects if we map into fibrant objects or fibrant. Don't know. Anyway, so we since we deal with since we're dealing with cofibrant objects at the moment, we want to define cylinder objects, and these are defined as follows. Oh, sorry, this doesn't make sense. Okay, what is I plus? I plus is the one-point compactification of I, where I is the unit interval. But the unit interval is already compact. So what does the one-point compactification do? Well, it just adds an extra point. Now, what is this space? Xn cross I plus, Xn wedge I plus. It's more or less the same as just Xn, sorry. What was supposed to do with this? Okay. Oh, good. Okay, so we'll take just the usual product Xn cross I, but we collapse collapse the base point cross I. Okay, so does this make sense? My first claim, which is pretty straightforward, these form these spaces form a spectrum. While we're at it, let me just mention that more generally, if I have a CW complex, then by smashing it with a CW, if I have a CW spectrum X, then smashing it component-wise with a CW complex, I get another CW spectrum. Why? Well, what happens if I take sigma xn, which the sigma xn smash y? well, I get S1 smash xn smash y. And this maps into xn plus 1 smash y, just by taking the structure map S1 smash xn into xn plus 1 and the identity map of y. Okay, so well, here we have a particular case. Instead of y, we take I plus, and we get another spectrum. So we are able to define left homotopy. Let's call this the cylinder of F. No, sorry, the cylinder of X. Then we say that. Two maps are homotopic if there is an F from the cylinder to Y, such that X X composed with the inclusion as the so X has two inclusions in X cross Y, same as for spaces. Let's know those 0 and 1. And so the homotopy composed with those inclusions should be F respectively G. So this is completely similar to what happens for spaces, but now we run into a problem. And the problem is, we have just mentioned that CW spectra are cofibrant, but they're not necessarily fibrant. And we know the reason. Basically, the reason is that after we transform those into maps from xn into omega xn plus 1, we may not get a homotopy equivalence. Okay, so So we there may not be enough maps between CW spectra. So So it turns out, which is something particular to the category of spectra. It turns out that it suffices for the maps to be it suffices to allow for maps of spectra to be determined, to be defined on cofinals of spectra, and not necessarily on the whole spectrum. Now, what does this mean? Let's see. We need to define cofinal subspectra. Let me first define cells of a CW spectrum. So we suppose we have a CW spectrum. And suppose we have a cell of some xm. Then the suspension of the cell will be a cell of xm plus 1, etc. And here it's important that that we take a reduced suspension. So when we take the reduced suspension, the zero cell, which is the base point, remains the base point, and all other cells become cells of dimension of the dimension one higher, and this is it. So we we define the dimension of the cell to be its dimension as a cell of xn minus n. So this this procedure gives the same answer for the cell and for each of its suspensions. It can be negative, yes. It can also be positive. And as we'll see in a minute, if we have a spectrum whose homotopy group vanish below some given degree, then this spectrum is equivalent to a spectrum without cells of the same dimension, where the dimension of the cell is given by this definition. Very well. And sometimes we will drop the x from the notation, and we will call this dimension the stable dimension to distinguish it from its naive dimension as a cell of xn. Now we can define cofinal subspectra. Well, first we need to define subspectra, but the definition of a subspectrum is straightforward. Now, a subspectrum subspectra and also CW subspectra. Both of those are defined in a straightforward way. Now, suppose we have a CW subspectrum X prime inside a CW spectrum X. We will say that X prime is cofinal in X if for all if for each cell of X, some suspension of the cell is an X prime. Well, observe that the inclusion of a cofinal subspectrum induces an isomorphism of the stable homotypic groups. Does everyone remember what these are? And why the inclusion induces an isomorphism? Well, it's the compactness argument. We need to prove that the map is the map of the homotypic groups is injective and surjective. Well, let's prove it's surjective. We represent an element of the stable homotypic group as a map into some xn. The stable homotypic groups are the direct limits. Well, by n of x is the direct limit of what? Can anyone tell me? Yes, by n plus I xi. Okay, so where the limit is taken with respect to the suspension maps and the structure maps of the spectrum. Very well. Each element of the direct limit comes from some finite stage. Well, an element of by n is represented as an element of by an element of by n plus I xi. Well, this element does not necessarily come from x prime, but some of its suspensions does. yes, from some finite x xi, and by compactness, the image of the map from the sphere is inside a finite subcomplex. Andrei, does this make sense? Very well. So after suspending sufficiently many times, each of the cells in the image will be in X prime. So we cannot guarantee that an individual element of pi n plus I will come from X prime, but some of its suspensions will. Alexei, does this make sense? Okay. Well, this shows that the map is surjective, and for similar reasons, it's injective. We just need to repeat this argument for a homotopy between two elements. If we have two elements in some pi n plus I, which vanish in the direct limit, then they vanish. At some finite stage pi n plus jxj. Very well. So there is a homotopy between the two maps. This homotopy only the image of the homotopy only intersects finitely many cells, which each of which, after taking a suspension, will end up in X prime. So, from the point of view of localizing with respect to the maps which induce isomorphisms of the homotopy groups, it doesn't really we don't really change the isomorphism class in the homotopy category if we pass from a spectrum to a finite subspectrum. So this map becomes an equivalence in the stable model structure. In the stable model structure, fibrations are complicated, co-fibrations are complicated. We'll talk about those, but the weak equivalences are very simple. They're just the maps which induce an isomorphism of the homotopy groups. So replacing a spectrum by a cofinal subspectrum does make sense from the viewpoint of homotopy theory. So we instead of B maps, we can define. No, instead of maps, we can define P maps. P for partial, and those are maps which are defined on cofinal subspectra. And P maps already suffice to localize spectra in stable weak equivalences, meaning if we take P maps up to homotopy, which is again allowed to be defined on a cofinal subcomplex of the cylinder, then we get maps in the homotopy category, which if both the source and the target are CW spectra. Okay, so let's consider this as a slogan, which will make more sense when we will have seen the model structure. Let me state a theorem. Suppose a theorem which illustrates the slogan. The slogan is just a slogan and shouldn't be taken too seriously. But here is one way to illustrate it. Whitehead's theorem. Suppose we have f(x) suppose we have a P map of CW spectrum. Okay, so I will have to write the conclusion on the opposite side of the board. So suppose we have a P-map of spectra which induces an isomorphism of the homotopy groups. Then F is a homotopy equivalence, meaning there is a map from Y to X, also a P map such that the compositions are homotopic to the respective identity maps. Well, before we prove the theorem, let's have a look at the statement and some of its implications. One thing this theorem tells us that if we allow P maps instead of just maps, then we are able to construct inverses of weak equivalences, and those inverses will again be P maps. So the localized category becomes a little bit less mysterious. If we allow P maps instead of maps, then we're able to invert the weak equivalences. So, in fact, if one thinks a little, then this theorem is not too far from the slogan. If we take into account that we have this observation, which says that the inclusion of cofinal subspectra induces an isomorphism of the homotopy groups, which means it's a weak equivalence in the stable sense. Okay, so before we prove the theorem, let's ask ourselves, do we understand what the theorem says? Okay, so are there any questions on what the theorem says? Well, let's first perhaps see a couple of applications. Okay, well, let's prove the result we already mentioned, a CW spectrum X such that CW spectrum X such that pi less than pi less than or equal n is 0 is homotopy equivalent to to CW spectrum with no cells of dimension less than or equal n. And actually, the proof is we first construct a weak equivalence, meaning a map which induces an isomorphism of the homotopy groups. And then Whitehead's theorem will give us a strong equivalence. So the Okay, so the homotopy groups vanish in degrees n or less, and we okay, so we construct for each I, where I is in some generating set of pi n plus 1, we construct representatives x and x what ki. So each stable each element of the stable homotopy group is represented by a genuine map of the spheres. So we we basically proceed in the same way as for spaces. For spaces, we have the same result. If we have a space with nothing, with no non-zero homotopy groups in degrees n or less, then the space is weakly equivalent or just equivalent if it's a CW complex to a CW complex with no cells in of dimension n or less. And it works in the same way for spectra, but it's easier because all pi n plus 1s and so on, they are homotopy groups, so there are no boundary cases when n is 0, 1, which have to be considered separately for spaces. Okay, so we start with a generating set for the homotopy group, and then we starting from those ki's may very well depend on I. And but altogether they give me a P map from the wedge of the suspensions of Sn+1 into X. Does this make sense? This map induces a surge action of on Pn+1. And then, firstly, does this make sense? We have this wedge, which may be gigantic, and for I equal 1, the map is defined on this suspension. For I equal 2, it may be defined on a different suspension, and so on. For n equal 3, there's another suspension, and so there is no single suspension which must work for every I. Well, it doesn't matter. We still have a partial map. If it doesn't make sense, please let me know. Okay, now I want to kill the kernel. The kernel, what do I mean? The kernel in pi n+1. Well, I basically do the same thing for each element of the kernel. I have a map. Well, let's call this x prime n+1. So for each element of the kernel, there is a map as n plus 1 plus k. Okay, let me erase this n plus 1. Okay, let me call this just a to make the notation clear. Then reach. There is a map as n plus 1 to ak. So what do I do with it? Well, well, let's call this map F. Well, let me. So for each element of the kernel, I replace it. I attach to A the suspension spectrum of the disk. Now let's see whether or not this makes sense. So what is this? Well, firstly, we may assume that F is cellular. So I need to define this thing, and the thing I need to define is only given starting from a certain stage. What do I mean? I mean I don't know the first k spaces of my spectrum, but I know all the rest. But it's the rest that counts. So let's just take our spectrum A, forget everything starting from everything up to stage up to the kth component, and then we have a sphere which maps into a k. So we can attach the disk using the sphere, and then we take all suspensions. So this spectrum is well defined. Starting from kth component. But we may ignore the rest. So, in particular, this thing may not necessarily contain all of A, but it doesn't matter as long as it contains all of A starting from some K. Andrei, does this make any sense? Jipping. No, AK is the kth component of this spectrum. We don't. This K may well depend on which element of the kernel we consider. For some element, K may be 2. For some other element, it may be 7, and so on. What's important is I have a map from A to X, and this map extends to this spectrum. A partial map extends to the spectrum. Why? I need to again allow to take suspensions. This map, it survives in AK, but it certainly does not survive in X. So it does not survive in some finite xi. Very well. So we again throw away all that comes before the I, and define the map on a subcomplex which on a subcomplex of this thing, which is allowed because I'm now talking about partial maps, P maps. Andrei, does this make sense? So, in other words, I may not be able to extend this to the whole of this spectrum, but it doesn't matter as long as I'm able to extend it to sufficiently high components. Okay, so let me just the P map extends to a P map. And so on. And this is where I want to say and so on. What does this mean? Well, this means we after we do this for a generating set of the kernel, we look at the spectrum we get. It has some n+1 cells and some n+2 cells, and it maps into X. Well, P maps into X, and the map induces an isomorphism on Pn+1. Well, then we'll look at what happens for Pn+2, and if the map on Pn+2 is not surjective, we add some more generators, and then we kill the kernel, and then we get some more n+2 cells if we need to add more generators, and some more n+3 cells. In other words, once we have the dimension, once we have the definition of the stable dimension of a cell, the proof is exactly the same as for spaces. And in some sense, it's even easier, because for spaces there is pi1, which is a group, but it may not be abelian, and there's pi0, which is in general not a group in any meaningful sense. Okay, I think we need a break. So before we have the break, are there any questions? If there aren't any questions, let's have a break, and then we'll continue.